So this is what we did yesterday, that we did discuss that rate is dependent on the concentration of the reactant or the reactants, whether it's X and Y colliding with each other. So A, B, and C. The power is the order of the reaction or the reactant. That you've got a zero order, which means that rate is not dependent on the concentration of the reactant. You have order 1, which means rate is directly dependent on the concentration of the reactant, which means if you increase the concentration of X, the rate would also increase proportionally. So, and order 2 is that rate is dependent on the concentration of the reactant, but it's a quadratic relationship, which means that if you double the concentration, the rate quadruples. So we discussed the graphs of these, how the concentration of the reactant would vary with respect to time. Now, when you have order 0, you get a straight line. That means the reactant concentration always decreases with time. I mean, as the reaction proceeds, the reactants get used up. So they're going to decrease. But the speed with which they're decreasing, the gradient remains constant. Because if the concentration of X decreases, the rate of the reaction does not change. So the speed with which it's decreasing, it remains constant throughout. And then you have order 1. In order 1, if the concentration of X decreases, the reaction slows down. It takes longer and longer time. It's faster, the change is faster at the beginning, but as the concentration of the reactant decreases, the reaction also slows down. That is order 1, that the rate of the reaction is directly proportional to the concentration of X. And order 2 is that if the concentration of X decreases, the reaction slows down by a much larger amount, which means that that if you halve the concentration of X, the rate becomes 1/4 because it's a quadratic relationship. So it takes longer and longer time. It slows down too quickly. So yesterday we discussed the half-life method, that all these 3 graphs, in order 0, the half-life always becomes half of the previous half-life. It decreases. The half-life is the time it takes for the concentration to decrease by half. Then the next time it decreases by half, that's the time required for that. And then it decreases by half again. So that is what the half-life is. In order 1, the half-life remains constant. For the first time the concentration decreases by half, it takes this much time, T1. Second time the concentration decreases by half, it still requires the same amount of time. The third time when the concentration decreases by half, it still pretty much requires the same amount of time. So the half-life in this case is constant. And then you had this order 2 reaction in which the half-life doubles. It takes longer and longer time for the concentration of the reactant to become half. The first half is quick because the reactant is present and the reaction is happening at a fast speed. And then it slows down. It takes a longer time. It doubles, the half-life doubles. The next time, the time required for the concentration to halve again, it's even bigger. So each successive half-life is double the previous half-life. So we did all of this, TK. Ibrar, is this clear?
Yes, sir.
The other thing that we discussed were experimental considerations, which we talked about, that most reactions have multiple reactants. So how do you investigate rate with respect to one of the reactant? You want to keep all the other reactants constant. And it's very hard to keep the other reactants constant, because if one of the reactants is getting used up, the other one would also be getting used up. So one way to keep the concentration of the other reactant constant is that you add it in large excess. So that even if the concentration of X goes to 0, you add so much of the other reactant that its concentration almost remains unchanged. Like if a tiny amount gets used up, its concentration still remains unchanged. So remember, when you're investigating variables, you want all the other things to remain constant. So during the reaction, how do you keep the other reactants constant? That is by adding them in excess. And we discussed a few points on measuring the. So we discussed a few points on how do you measure the concentration in an experiment. So anyways, now we're moving. So one of the method is this graph method. Now, what we're moving towards is we're going to discuss order 0, 1, and 2 with respect to like we did 3 orders, right? It's order 0, 1, and 2. And we're going to relate this to the mechanism of the reaction. So we're going to talk a bit about mechanisms, like why is there an order 0? That's the question. For example, if you have two reactants, and let me give you a real idea, example. Now I've got so I've got this halogenoalkane, and it's reacting with OH ions. And there's a substitution reaction, which is nucleophilic substitution. This is something that you did in your AS as well. So anyways, the nucleophile, which is OH, there's a C over here, and then there's Cl. So anyways, the Cl gets displaced by OH. So that's a simple, straightforward reaction. Now the issue, now it's got two reactants. It's got reactant number 1 and reactant number 2. So it's got these two reactants. You've got this and you've got this. Now the rate depends on the concentration of both of these reactants. Like you have this reactant colliding with this other reactant. And due to the collisions, there's going to be a reaction, right? So the rate is dependent probably on both reactants. So rate depends on the halogenoalkane, and it's Cl. Its concentration, and it also depends on the concentration of the other reactant, which is OH minus 1. But when it comes to the order of the reaction, this is order 1, while this other one is order 0. Now, what order 0 indicates, I mean, what this thing represents, order 0, means that the rate of the reaction is actually not dependent on this. Like anything to the power 0 is 1. So it basically disappears from the expression. So that means rate is only dependent on the concentration of this reactant. It's not dependent on the concentration of the other reactant, because it's 0 order with respect to OH minus 1. So the question is, how could something be 0 order in the first place? Like if I increase the concentration, so let's say I increase the concentration of, one second. So if I increase the concentration of OH ions.
Sir, ये order 1 or 0 का फिर से explain करें. How does it affect? It's only affected by CCl or not by OHEQ?
नहीं, order 1 का पता है क्या? What is order 1?
नहीं, ये थोड़ा सा recap करते हैं.
Order 1 was that rate is, I mean, if something has power 1, what is the relationship? It's directly proportional, right? Like you increase the concentration of the reactant, the rate should increase as well, right? Clear?
जी हाँ जी, ठीक है.
Order 0 indicates that rate is not dependent on the concentration of X, because anything to the power 0, like whatever concentration you put over here, power is 0. That means it's going to come out to be 1, right? So the rate would remain unaffected by that, by whatever the concentration of X is. Is this clear?
Yes, sir. जी.
And order 2 indicates that rate is dependent on the concentration of X, but the order is 2. That means like if you double the concentration of X, the rate quadruples. If you halve the concentration of X, the rate becomes 1/4. ठीक है? Is this clear?
जी, ये भी clear है, ठीक है.
Or a relationship which is rate is dependent on the concentration of your reactants. So A and B, the powers are your orders. They did, I mean, they they determine the relationship. Like, what's the relationship? Is it directly proportional, or is it not going to have any effect, or is it going to have a lot of effect? Okay, is it going to be order 0, 1 or 2? Okay.
जी ठीक है.
Anyway, so in this case, I mean, these orders are already given. Okay. So the point I'm trying to make is, how does order 0 make sense? Like, if you increase the concentration of the reactant, the collisions would increase, so the reaction should speed up. But order 0 indicates, what does it say? What does it? It states that if you increase the concentration of X, so if you increase the concentration of X or decrease, not of X, of OH minus 1 in this case, the rate of the reaction remains unchanged. It does not change. Now the whole point is that all your life you've studied that increasing the concentration speeds up the reaction. So over here we're increasing the concentration, but the reaction 0 means it's not speeding up. So why is that? Because reactions are not that simple. I mean, we always write an equation. An equation shows the reaction happening. An equation always shows the overall reaction. Most reactions happen in multiple steps, and the same applies to this reaction as well. So remember, by just looking at the reaction, you're not able to figure out what the relationship is unless you know what the mechanism is. Now, if I draw the mechanism of this reaction, the mechanism of this reaction is something like this. It's so the mechanism of this reaction is that it's got 2 steps. There's step 1 and there's step 2. I mean, if you remember the Sn, I think this is the Sn1 mechanism for tertiary halogenoalkanes. So if you remember the Sn1 mechanism, it's going to show you what it's going to show you is that first the halogenoalkane, which is CH3, and CCl. The OH is not involved in the first step. So due to random collisions, the Cl, it dissociates or ionizes. I mean, I can draw the whole structure. It's better to actually draw the whole structure. You got a CCl, and you've got 3. Now, the first step of the mechanism is the Cl dissociates, and that results in the production of a carbocation. And the Cl minus 1, it breaks off. And that's a slow step. It requires, I mean, there's going to be a lot of collisions, and only after that is the Cl going to break off. So that's kind of a slow step. But as soon as the carbocation is formed, the OH ion comes in and attaches itself to the carbocation. So the OH minus 1 is now coming in. That's your nucleophile. And it comes and attaches. I said, no point in understanding the mechanism at the moment. I'm just drawing the mechanism. This one is a fast step.
So tertiary Sn1 mechanism was for tertiary halogen alkanes, right?
Yes. I must ignore that. Forget the mechanism. I'm writing down the mechanism. That's how the reaction is happening at the moment. and you get the alcohol. So that's, and the alcohol is formed. The OH comes in and takes its place. Now, this is overall what's happening. You've got a fast step, you've got a slow step as well. You got a fast step, you got a slow step. Now, the point I'm trying to make is, how does zero order make sense? Like, why is, you got two reactants, and I'm going to circle those two reactants. The mechanism is slightly more complicated. So I've got, I mean, this is one of my reactants. And this is my other reactant, which is OH minus 1. As you can see, both reactants are involved in different steps. In the first step, there is no OH ion. OH ion doesn't even have a role to play. In the second step, you got an OH ion coming in. So that's the overall reaction. And let's assume the slow step takes 100 seconds. And our fast step takes 1 second. So there could be a number of reasons for that. But let's, at the moment, don't go into that much detail. Let's say this slow step is taking 100 seconds and the fast step is taking 1 second. Now, if I increase the OH ion concentration, which step would speed up? The fast step or the slow step?
The slow step?
Okay, because why would if I increase the OH ion concentration, why would this step speed up? I mean, this step has nothing to do with OH ions. Ibrar, is this clear?
Yeah. Right.
So which step speeds
so
up?
So it will speed up the second step.
Because the OH is involved in the second step. So there would be, if I increase the concentration of OH ions, there's going to be more collisions between them because there's going to be more OH ions, and the fast step would speed up. So fast step speeds up. Let's assume that I increase the concentration of OH ions by 1,000,000 times. Like, I add a lot of OH ions, right? So obviously the reaction is going to speed up by a much, I mean, it's going to become really quick, right? So it speeds up. So at the moment it's taking how much time? So it goes from 1 second. I mean, it was taking 1 second, but now I've sped it up. So now let's say it's taking 0.0001 second, right? So now it's really fast. Is this point clear up to this point? Zaib, is this clear? Hafsa, Alicia, Zoha, is this clear?
Yes, sir.
Yes, sir.
Acha, so the second, so I mean, just this point that the slow step has nothing to do with OH ions. So if I increase the concentration of OH ions, the fast step would speed up. But what will happen to the overall speed of the reaction? The overall reaction is the sum of the two steps. I mean, you want the first step to happen and then the second step happens, right? So at the moment, the overall reaction is also going to speed up, but by what amount? So what's the overall speed? Previously, it was taking how much time? It was taking 101 seconds, right? I mean, why was it taking 101 seconds? The first step took 100 seconds. And after that, the fast step took 1 second. So it was taking 101 seconds. How much time is it taking now? Like, I've increased the concentration of OH ions like 10 times or 20 times or 100 times. Like, I've really increased the concentration of OH ions. So now the 100-second step is still taking 100 seconds, but the 1 second step is now taking 0.001 seconds, right? So the overall speed goes from 101 seconds to 100.001 seconds, right? So what difference did it make? Like, I increased the OH ion concentration, the overall speed of the reaction hardly changed. It went from 101 seconds to 100.001 seconds. Even if I keep on increasing the concentration of OH ions, like if I continue to increase the concentration of OH ions, I add more OH ions, would there be any difference on the overall or noticeable difference on the overall speed of the reaction? Like I keep on adding more OH ions, this reaction speeds up even further. And it would go from 101 to now 100.0001 seconds, right? So the point is, if you're trying to speed up the fast step, the overall reaction is not, the effect on the overall speed of the reaction would be negligible. Is this point clear to everyone? Nadine, Sam, is this clear?
Yes,
Marius?
sir.
So, clear? Is this clear, this point? I mean, that's the important point.
Yes, sir.
Okay, so the point is, if you're trying to speed up the fast step, the reaction is not going to speed up. I mean, the fast step will speed up, but speeding up the fast step will have almost no noticeable change on the overall speed of the reaction. So that means the order with respect to OH ion is zero order. That means you keep changing the concentration of OH ion, the overall speed of the reaction hardly changes. It doesn't change. So the rate of the reaction is not dependent on the fast step. So that's point number one that we're going to write down. So the first point that we have figured out is that any reactant that's involved in the fast step, that's zero order. So point number one is any reactant in fast step has order zero. And in no point changing its concentration, this reaction is not going to speed up. And then let's do the same thing, but now let's do that to the slow step. So let's do exactly the same thing. Forget OH ions. OH ion is not speeding up the reaction. So let's do exactly the same thing. And if I increase the concentration of this halogenoalkane, if I double the concentration, there's going to be more collision. The reaction would be faster. So all of us say, like if I double the concentration, the reaction speeds up. And it's now taking 50 seconds, right? So now what happened to the overall speed of the reaction? It went from 101 seconds to 51 seconds. So all of a sudden the reaction is speeding up. So that indicates that any reactant that's involved in the slow step is your rate determining step. So the rate of the reaction depends on the slow step. So slow step is known as the rate determining step. So that's known as your rate determining step. And any reactant involved in slow step is order one, which basically means that the rate of the reaction would depend on it. And we should also add that the coefficient in the slow step would become the power. So coefficient, one second. It becomes the order. So is this point clear that that reactions, so I'll just sum this up, that reactions are not that simple. Like if you write an equation, the reactions don't happen that way. I mean, whenever you see an equation, that's the overall reaction. Reactions normally happen in multiple steps. And when you have multiple steps, then what happens is that some steps would be fast and some steps would be very slow. So the rate of the reaction depends on the slow step. Like if you're trying to speed up the fast step, the reaction overall is not going to speed up. If this takes 100 seconds, this takes 1 second. Speeding up this step is not going to affect the overall speed of the reaction. So any reactant that's involved in the fast step, it will remain sorry. So any reactant that's involved in the slow step, any reactant that's involved in the fast step would remain, the rate of the reaction would not depend on that. And any reactant that's involved in the slow step, the rate of the reaction will depend on that. So this would be order 1, and this is going to be order 0. Is this clear?
Yes, sir.
TK, everyone else, is this clear?
Yes, sir.
Yes, sir.
So then we're going to add another thing. So how do we get order 2 then? So let's talk about a reaction that has order 2. Now order 2 means so I'll for order 2 I'll do a simple reaction, but I'll a made up reaction. Like it's not a real reaction. I'll just make it up right now. So there's a reaction in which there is and this is for order 2. Like how do you get order 2? And it's the same logic. Like if you increase the concentration, like if I increase the concentration of one of the reactants, like if I double the concentration of one of the reactants, the collisions should also double, right? I mean, directly proportional makes sense. But why is the reaction, like if I increase the concentration of one of the reactants, why is the reaction speeding up 4 times? Like that doesn't make sense. Why is there a quadratic relationship? So we'll discuss that now. So how do you get order 2 now? So here's a reaction, the overall reaction, it's 2NO, and they're reacting with Br2.
Sir, how do we know the rate of reaction is increasing by quadruples? I mean, by 4 times.
By?
आपको कैसे पता चला?
वो graphs है ना, like if I made the.
I mean कि कैसे पता लग रहा है कि the reaction is increasing by either I mean that.
But simple enough. If I let's assume
नहीं
that
graph नहीं given. अभी आपने कहा कि this reaction would proceed through order 2.
yeah, I'm just trying to explain order 2. Okay. Let's say it's given that this is. I'll explain just in a bit. Okay. I'm just saying कि how do you figure out, like figuring out order 2 is easy. Like if I double the concentration of Br2, the reaction, if it speeds up proportionally, that means the order is 1. If I double the concentration of Br2 and the rate of the reaction, or the time by just timing the reaction speeds up 4 times. That's order 2. Is that clear?
Yes.
Okay, figuring out order is very easy. Like Br2 concentration is doubled, and let's say the rate of the reaction remains unchanged. That's order 0. Br2 concentration is doubled, and the rate of the reaction also doubles by using a stopwatch. So that's order 1. Doubling concentration of Br2 and the rate of the reaction becomes 4 times. That's order 2. Okay, so figuring out order with respect to each of the reactions, that's kind of easy. So I'm just going to explain like where does order 2 come from according to the mechanism. So let's say this reaction has this mechanism that there is NO. It first reacts with Br2 and it goes on to produce 2 things are produced. NOBr is produced, and then you have a Br atom is also produced. Then another NO, nitrogen oxide molecule comes in. And the Br that is produced in the previous step, it reacts with it, and another NOBr is produced, right? So that's the two steps of the mechanism, which step 1 and step 2. So that's how this reaction is happening. NO reacts with Br2, produces NOBr, that's one NOBr produced, and the Br that's left then reacts with the other NO and produces NOBr. So remember, this is just a made up mechanism. So let's assume that the second one is the slow step. And the first one is the fast step. So what did I tell you? That rate of the reaction is not dependent on anything that's in the fast step. It's dependent on reactants that are involved in the slow step. So that means in this case, the rate of the reaction depends on NO concentration and Br concentration, right? Because if the slow step speeds up, the overall reaction speeds up. So if you increase the concentration of Br or you increase the concentration of NO, the reaction would speed up. Okay, is this clear? Is this clear up to this point?
Yes, sir.
Yes, sir.
So again, we're not getting order 2 at the moment. But if you look at this carefully, you would notice that this Br over here is an intermediate. It's not your reactant. Like Br is not a reactant. I mean, your original equation, there is no Br, there's Br2. These are your two reactants. Br is an intermediate that was made in the previous step. So Br over here is actually an intermediate that was made in the previous step. So when I say that the rate of the reaction depends on the concentration of Br, what I indirectly mean is Br itself is dependent on the concentration of NO and Br2 because Br was made in the previous step. I mean, if the concentration of NO and the concentration of Br2 is high, then the concentration of Br would be high. If the concentration of NO and Br2 is low, then the concentration of Br that is produced would also be low. So the point is, when I say that the rate is dependent on this intermediate, then it's kind of indirectly dependent on the previous step as well. Because it's an intermediate, when I say that rate is dependent on the concentration of Br, Br itself is dependent on the concentration of Br2 and NO. So I should replace Br by NO and Br2. Again, let me explain this quickly. That in the previous case, we discussed that the rate of the reaction depends on the slow step. It depends on the concentration of NO and Br. So that's fine up to this point. But Br's concentration, Br was an intermediate that was made in the previous step. I mean, that's where the Br came from. So if I say rate of the reaction depends on Br's concentration, then Br's concentration itself is dependent on the concentration of these two things. Their concentration would be high, then Br concentration that is produced would be high as well. So when I say that rate of the reaction depends on Br, what that indirectly implies is that the rate of the reaction depends on the concentration of NO and Br2, because those two reacted to produce Br. So your rate expression would be this, like you're going to replace the intermediate with the NO and Br2. Is this clear, this thing?
Yes, sir.
Okay, is this clear to everyone else? Sam, Nadine, is this clear? Afza, Alicia?
Yes, sir.
Yes, sir.
So now your rate is, how many times is NO appearing in the expression? That's 2 times now. So that means if I combine all the terms together, rate is going to be dependent on NO's concentration, but now it's order 2, it's going to be squared. And for Br2, it's order 1. So what does order 2 indicate over here? What it indicates is that if you increase the concentration of NO, remember the slow step. If I increase the concentration of NO, then because of the higher concentration of NO, the reaction would speed up, right? But if I increase the concentration of NO, the concentration of Br would also increase. So if I increase the concentration of NO, not only would NO increase, but the concentration of Br would also increase. So the reaction would, like if I double this concentration of NO, the reaction speeds up, the collisions double. But because of the concentration of NO, Br's concentration also doubles. So the reaction doubles again. So order 2 indicates that if you change the concentration of one of the reactants, two of the reactants in this slow step would have their concentrations doubled. Is that point clear? Is this clear? Zoa, is this clear?
Yes, sir.
Okay, so that is what is meant by order 2, that that the collisions would become 4 times. Like this would double, but because of NO's concentration, Br would also double. So Br would also double. So in the slow step, 2 of the reactants, their collisions would double. So it would become 4 times. And Br2, with respect to Br2, it's order 1. So if I increase the concentration of Br2, let's say I double the concentration of Br2, the concentration of Br that is produced would also double. So in my slow step, only one of the reactants is actually doubling. So that is order 1. And the reaction would speed up proportionally. But with NO, it's going to be order 2. It's going to be a quadratic relationship. So remember this. When you're dealing with mechanisms, replace and trace intermediates. Present in the slow step. So don't allow any intermediates to be present in the slow step, like these two. Replace Br2 on with NO and Br2. So anyways, so it's order 0, 1, and 2. Order 0 is if you're given a mechanism, any reactant that's involved in the fast step, the rate of the reaction is not dependent on the concentration of that particular reactant. Speeding up, you increase the concentration of OH, the fast step speeds up, which is not going to speed up the overall reaction. So rate over here would only be dependent on the reactant that's involved in the slow step, which is going to be this one. So any reactant that's involved in the slow step, that's order 1. Any reactant that's involved in the fast step, that's order 0. And how do you get order 2? You get order 2 when something like this happens. If this is the slow step, then rate is dependent on these two. This is an intermediate Br, and the Br itself is dependent on the constant Br2 and NO. So NO comes in twice. So by changing the concentration of NO, 2 of the reactants in the slow step, their concentration changes. NO affects the concentration of Br, so Br's concentration increases. At the same time, NO's concentration itself is increasing. So 2 reactants, their concentration changes. So let's do this in the next class as well. We'll do more mechanisms, but is this all clear? This thing?
Yes, sir.
Okay, so we'll practice a bit more.
Yes, sir.
We'll practice a bit more in the next class. The same thing, mechanism. Otherwise, we are done with mechanisms. Okay, by just looking at a mechanism of a reaction, and if you know which one is the slow step, you can figure out the order of the reaction or the reactants. So we'll try and practice more questions, but in the next class now. Okay, so let's continue in the next class then.
Thank you, sir.
So thank you, sir.
Take care, Allah Hafiz.
Thank you, sir. Allah Hafiz.